So yesterday, thanks to one student who asked me about the shear that is generated at the middle of a beam. So I checked the some references. So this happens when we both have bending and shearing at the same time. I didn't cover this at the beginning. So when this is happening, I'm gonna explain what's going on. The tau right here, basically we can call it transverse shear. So it's a horizontal shear at the middle of the beam. Now, what's this guy? Basically, we have a beam, a long beam, and we made a small cut right here in the middle. So we are observing this particular cut. And we need to deal with transverse shear when there's both bending and shearing. So meaning we have shear, the change of shear on the left and the right hand side of that cut, and there's a change of your moment from left to right. When that happens, there could be shear at the middle, horizontally. Why didn't we discuss this? And how about cylindrical geometry? No matter it's a rectangular cross-section or cylindrical, a circular cross-section, the concept remains the same. But the issue is, most of the time we were talking about a point where we have a great deal of compression or tensile. So let's say I have moment bending this way, then I have the tension right here. We have normal stress left and right. And after I tell you about this transverse shear, on the point at the top, this goes to 0. So when we are only talking about the stress condition at this position on the top, we don't need to worry about transverse shear because it's 0. However, in my exam, we were talking about the point on the side. When we do that, actually, this plays a role. So my exam, the last problem in the exam, in fact, we need to talk about it, but I never cover how to do it in the lecture. So for the exam, I will not count. I will give you the point for that particular small problem. But now I will be talking about how to calculate this transverse shear. So what's happening is we need to review what we did earlier right here, where we don't worry about the thickness. We only study this like a plane, and at the time we have balance of moment, and then we derive those equations. This one will be used later on. So, and also we use this when we try to draw the shear diagram and the moment diagram. We quickly got the shear diagram, and then we took an integral, so we were able to get bending moment. So this was used for several times, and it will be used later on. Why did I say this only happens when we have both shear, change of shear, and change of moment? Because later on, this equation will depend on the value right here. If this is 0, then the transverse shear will be 0. So in what situation this will be 0? If you have constant moment all the way, then every time you move your X, your moment doesn't change. In that case, there's no shear. If there's no shear, then you don't have transverse shear. Okay? So, only for the case we can so-called the pure bending. Then why does people call pure bending? Pure bending usually is used to describe bending everywhere but constant value. So it's like you bend something and you apply equal bending moment everywhere. When that's the case, then no matter where you are, your moment doesn't change, so that doesn't generate a change of your shear. If this is 0 later on, I will let you know, this becomes 0. So if we have a problem that's pure bending, we also don't need to talk about transverse shear. However, in the homework and the exam, both problems were not pure bending. So theoretically, we need to talk about it. However, if we are only talking about the very top point, then it's not an issue. Okay, so let's continue on this part. So right now you may need to understand what's going on. Now I view this same cut in a three-dimensional way. Here I need to observe its thickness. So the width right here is B. As we usually use, the distance from the top from the neutral axis is C. So C right here and C, also C at the bottom. And also we made a cut, a green one. The height of the cut is having a distance of Y1 from its plane to the neutral plane, neutral axis. And the horizontal distance is very small. It's a small cut, so width is dx. Now I put some stresses on the drawing. We are mainly talking about a smaller cut above the green plane. On the left edge, there must be some normal stress. On the right edge, there will be same normal stress pointing in the opposite direction. However, the stress could be different. There's a change of the stress. Okay? And if you only observe this cube, it's not a cube, this cut, at the bottom there could be shear. So when we talk about transverse shear, it's about this cap, this cut, right in the middle between the upper part and the lower part on that green plane. Okay? So if we try to do a force balance, we can get there's something called Fn, Ff. What is Fn and Ff? So the reason why my book used N and F is like nearest surface and the further surface. So this is the N side and this is the F side. Okay, that is just a symbol. Okay, so if we want to compute the total force that is related to the stress right here on the left edge, basically you can do an integral of the stress and then multiply the area. So if your stress, so this is a general approach. If the stress is not constant, it's like there's a distribution. In general, you need to do this, okay? But if it's a constant value, then you can just multiply the area. And the force on the right basically is the stress multiplying the area, okay? Now, what we can do right here is to recall one equation. We already know if we have bending and we are like at the top So the stress would be m, here I need to use my over I. I need to be very careful what is my y. Is it y1? Let me see. Oh, it's a function of y. So basically the stress of any position, could be computed by this equation. Earlier we had mc over I, but this time I would like to know the stress everywhere. Then it's a general equation. So we can plug it in. When we do that, the m over I is a constant. Only thing left would be y left inside the integral, because the area is depending on your position of y. Okay? So similarly, you can do the same thing right here. But this time, you would have m plus dm over I. Because here you do have an increment of your stress. So from the same equation, you should have your increment of your moment right there. Now, by balance of force, I need to compute the force at the bottom. So here there's a FB. So B represents bottom. Okay, so between lying on that ring plane, FB would be the stress that you're looking for multiplying the entire area. So the area would be the width right here times the thickness right here. So it's gonna be B dx. Right? So there's a balance between them. This studying this chunk, these are the three forces that was applied onto this chunk. So we will know the Fn plus your Fb, that both goes to the right, equals to your Ff. So at the end, Fb is going to be tau b dx, and Ff minus F, you can see some common terms. They eliminate each other. So the remaining term will be dm over I, and then integral y dA. So from here you can tell tau can be computed. It's actually dm over dx, and then b multiplied I right here, and then integral y dA. Okay? That's the general equation. And from here you can tell this guy is exactly V. Okay? And that's the reason why I said if there is no change of your moment, this becomes 0 and there is no transverse shear. Okay? And also, if we can try to solve this, and then you will realize at the very top, this is 0. So let's try to solve this. I don't like this one. So this is V actually, and this is BI. And the integral, so where exactly are we doing the integral? We are actually studying whatever that is inside this box, right? So we are taking the integral from y1 to c actually. That's what we are doing. And this is actually the first order moment of area, or area moment. Okay, so in the past we have I equals to y squared dA. This is the second order moment of area. So it's the difference is this is a first order term, this is like a square term. Okay. Now, so to continue, you need to do some math. Let's work on for rectangular geometry. So if it's a rectangular geometry, you are dealing with a shape. And let's say I put some coordinates here. Here's your x, here's your y, and here's your z. Okay? So it's like you are viewing the whole thing. Actually, it doesn't. I just want you to know where I'm looking at this guy. So this is your x. So that actually in what I'm drawing there, this is actually z, this is my y, and my x is right here. So it's like I'm viewing from the right hand side, and this would be 2c, and this would be b, right? And we know for I, checking on the horizontal one, it's a 12 BHQ, right? BHQ. So BH cube, right? So this is actually 12, 8 BC cube. So it's actually 2 over 3, okay? And we are working on so this reminds you what is I for rectangular following our coordinates here. So tau will be V over B times I. I is over there. Right? Okay, so and then doing the integral. So y here, d. You want to do dA, so for the and dA is going to be when we were working on this. So basically dA is this area. Okay, this is actually dA. So that would be B times the height. No. We are only studying one slice actually, because we're taking the integral. So dA is only one slice. Sorry. So, because we are summing everything up. So this is one slice. This is dA. Okay. So the height is dy. Height is dy, and the width is b. So here is b dy. Okay. This was dA. Okay. The exact one that I draw on the left, and then we are taking integrals. So we are studying from this position to the very top. So that position is actually y1, and the very top is c. So if you do the whole thing, and you can get the general equation of this. So I did the math already. This at the end would be 4, 3, V, B, C, cube, C squared minus Y1 squared. Okay, that would be the final equation. But where at Y1 equals to C, that's the position on the very top. You realize C squared minus C squared over there. So the transverse shear is 0 at the very top, based on how we calculate this. And where is the maximum value? When y1 is 0, basically on the neutral plane, we have maximum value. So tau has max value, and this equals to CV 4BC cubed, so C squared here. So at the end, 3V 4BC, okay? And some of you may study this and found this in a different form, because usually they want to put area at the bottom. So the area is, they would like to use a cross-section area. So this geometry has a cross-section area of 2BC. Okay, if I define A as 2BC, then this is going to be 2A 3B. So this is what you usually see from a book. But in fact, the transverse shear is always changing from the middle, between the middle and top. So if you would like to make a drawing of it, actually the transverse shear looks like this. Okay? So at the middle, it's actually having the largest value. And that's also why when we are at the top, very top, we usually don't need to talk about transverse shear, no matter if you have a change of bending moment, because this is remaining 0 at the very top. However, if you are talking about somewhere at the neutral plane, then it's a different story. Now for circular cross-section, so to match the coordinate that I show over there. So if the radius is r, and from the past we already know I of this guy, so basically I along the horizontal coordinates, I is pi r to the 4th over 4. You can check, you can try it by yourself. The integral for circular geometry is more complex, but it's still doable. Now I have I here, so I should put my I here. So here is pi r 4 over 4, okay? And doing the integral, exact same thing right here. So from y1 to basically now to the very top. So the distance from the neutral plane to the very top is actually r, okay? And you are going to have y times dA. So what is dA? So the issue about circular geometry is that dA is harder to calculate. So over here, this is your y1. Here's your dy. And the area right here is dA. It's changing from different positions. So how do you get it? So one way to get it is to use r right here, and the distance right here is actually square root of r squared minus y1 squared. So the width is gonna be 2 times r squared minus y1 squared times the height dy. Okay, then you can do the integral. So how to solve it? We can use the geometry right here. If I say this is theta, then what's the equation I'm gonna use? Sine theta is gonna be y1 over r, right? That's sine theta. That's very useful for me because I can convert this whole thing to the following. I can have 4 and a 2, so I have an 8 right here. V B pi r 4th, same integral, And here I can have my y. Now I can convert this into 1 minus sine theta squared, but I took 1r out. I took 1r out, so I should have to the third one, right? If you take 1r out, then this is only q at the end, and dy. So next what you need to do is to convert everything to theta. So y1 equals to r sine theta. So we can convert everything here to theta. You need to know what is dy. dy basically is going to be r cosine theta d theta. So by doing so, you can have d pi r to the third. Y is r sine theta. This is going to be, this is basically cosine theta, right? So cosine theta. And dy is going to be r cosine theta d theta. Okay. So it turns out it becomes an integral of theta. And you are taking integral from y1 to the top. So you can call this theta as a theta 1. So basically you are taking the integral from the angle of theta to the very top. At the very top, the angle is going to be 90 degrees. Okay. So by doing so, you will be, I did the math already. So at the end, it's going to be AVB pi r half negative cosine q, and then from theta 1 to pi over 2. Okay, that would be the final, we can try it, the final equation. And we would like to know, similarly, at y1 equals to r, when you plug in, you realize, actually, from now on, we don't talk about y anymore, we talk about theta. So at theta 1 equals to half of pi, it's like at the very top. When you do that, shear becomes 0. So same as the rectangular one, at theta 1 equals to 0, basically, if this is 0, that you're talking about the neutral plane. So at the end, I did the math already, it's gonna be 4v over 3 pi r squared, or sometimes people would like to use 4v over 3a. So a over here is the entire area of the circular cross-section. So what you usually get is 4v over 3a. Okay? So that answers someone's question from yesterday. So back to our problem. When we are dealing with a point right here, then we do have shear, shearing horizontally. So you do have shear like this, and because shearing force comes with a pair, so it goes up here, it goes down here. So if you want to do more circle analysis, then your material looks like this. And the magnitude of this shear force, shear stress, basically is you can use 4v over 3a. Okay? And you do have a shear diagram. You know the v, so you can use 4v over 3a to compute how large it is. And the more circle would be something like this, because there's no, at the neutral plane, there's no normal stress anymore. So it's going to be a point here and another point here. One goes clockwise, the other one goes counterclockwise. So this is gonna be your Moore circle. Okay, and if you want to compute principal stress, you still have principal stress first and the second one positive, one negative, and the maximum shear is gonna be 4V over 3A. Okay, so if you truly want to get the final problem from the exam, I think this is how you get it. Okay, so that's a quick answer of yesterday's question. So any following question? Yeah, go ahead.
So the depot has zero density.
Say again?
The depot has zero density.
I didn't get it.
At a 0 point. At the
At
depot.
a zero? At a zero?
The D.
D, what do you mean by D?
In the exam. The top.
Ah, yeah.
0.
So this is just like the exam, right? So at the top is just like how you solve the usual problem. You use this equation. But at the side, there's no normal stress. However, on the side, there should be transverse shear. So one student sit here, asked me, there should be shear, right? So that's why I studied this. I realized, yes, he was right. When there is change of moment at the neutral plane, there's actually everywhere inside this cross section, there's horizontal transverse shear. It's everywhere. However, at the very top, that shear is 0. Okay, so when we are talking about the point on the side, actually that's on the neutral plane, and that's where we have the largest transverse shear. And the magnitude, it can be computed by that exact equation, 4V over 3A. If you are looking for, let's say, you are studying some other point at any height, all you need to do is to plug in the equation right here. Because this is like the height that for your investigation. If you want to study a different level, the equation gives you the transverse shear on that particular level. So all you need to do is to find out on that particular level what's the corresponding theta one, and then plug in the theta one. You can do this, complete this calculation. So at the end, you will get something different other than 4V over 3A. It will be some other value, but that would be the transverse shear on that particular level. Okay.
At the middle part.
At the middle, yeah.
There's only transverse shear or normal.
Yeah, because on the neutral plane, if you are doing bending, then the bending only affects anywhere outside of the neutral plane. So the bending generates normal stress. If you bend this like this, on the upper part is like a normal like tension force. At the bottom is compression. But on the neutral plane, there's no normal force. So on the neutral plane, we do have, if we are standing here, the right-hand side will pull your upper part, and the lower part will be compression, right? If you are bending like this. But right in the middle, there's no normal stress. So usually when we draw the shear diagram and the moment diagram, we care about what's the moment, bending moment. And at this particular position, at the very top, the stress equals to moment times the radius over I. So from the shear diagram, we get the value of moment. But you can have stress at any position. However, if you are standing in the middle, the radius is 0. That's why in the middle, no stress, no normal stress. only from the edge. So usually when we are dealing with bending problems, we usually care about the point on the very top. And usually when we do that, we don't need to care about transverse shear, because transverse shear at the very top is 0. However, in my exam, I asked you about the point in the middle. I was thinking about this diagram only. I forget about this guy. So that student was right. When we are talking about somewhere in the middle, don't forget about transverse shear. And this was not covered from the past. I didn't prepare a PowerPoint, so I need to write it down on the board for today. Okay, so okay, no time for the next model. I'm sorry. This is taking a while. I have to shift the maximum distortion energy model to the next lecture, because today's lecture is only 1 hour. But today I should be giving you a new homework. I would like to shift that homework to next week as well, because in the homework 2, I want you to solve another beam problem. But in the problem, I would like you to use maximum shear stress model, maximum strain energy model, and the distortion energy model to see the difference. So I cannot give away the homework today, because I haven't announced I haven't completed the maximum distortion energy model this week. So I will give you the homework next Tuesday. Since we still have some time, any questions about what I did? So the tricky part of this math is actually right here. How you can change your coordinate from y to theta, and how you deal with this. So over here you will have sine times cosine squared, and that's quite troublesome to handle. I actually just got the solution from internet, so I didn't spend time on truly solving it. However, that would be somewhere that could take you some time if you truly want to try the math. So this integral is not too straightforward. You need to figure out how to do it. Also, if you are trying to solve for the second area moment of inertia. If you truly try to solve it, you will face similar analysis, but inside the integral is going to be sine squared times cosine squared. Because for the second one, you have y squared right here, so you will have one more sine right here. So to solve for this, you need to deal with sine squared, cosine squared. Similar integral, but this one is sine times cosine squared. This one you will face sine squared, cosine squared, and that needs some trick to you need to simplify. Any other questions? So who was the student who asked me the question yesterday? You didn't come. Yeah, go ahead.
Is there a difference between this formula and the formula you give us?
I have never. No, that's another story. So in this problem, we never talk about torsional shear. This is pure bending and due to some reason, you have some forces somewhere, so there is shearing force up and down. And if you are putting torsional shear stress to the problem, then you use the equation I gave you. So the most complicated problem could be having everything together. So just like the first homework, actually. So in the first homework, we had a pulley going this way, and then we have pulley going this way, right? Those are the pulleys. And then we had supporting reaction forces from the bearing. So these are bearing. And these are pulleys. So in this particular problem, because the force over here generates, I don't remember which direction, generates some kind of torque right here, and this over here, there's another torque. So this geometry is being twisted, torsional shear. And the torque we computed tells you how much shear you have. So the shear force equals to 16T over pi d cubed. That shearing force looks like this when you look at the cross section. So it's like this, shearing stress. And this is 16T over pi d cubed, okay? So the shear is everywhere. Now, in this problem, we also have bending moment. So this is one phenomenon we need to deal with everywhere. Second phenomenon we need to worry about is where we try to draw the shear diagram. I remember this problem looks like I think it was like this. If I'm right. I remember the shear looks like this, and the moment looks like it's negative, so it looks like this. This was the moment, okay? So we said, okay, this point has the maximum bending moment, so we know somewhere over here we do have normal stress of m radius r over I. So this is the second thing that we need to deal with. And if this is located at the very top, then on the cross section, on the very top, we do have you're observing from top. Your eyeball is right here. You're observing from top to the bottom, and then it's like you put a small plate right here, and you realize there's shear going this way. And for bending, if we are dealing with a very top point right here, then it's like you are bending. You're bending this way, so you should have normal stresses going toward the side. So it's like pulling like this. So if you observe, if you make a drawing like this, and you're viewing from the top, you do have normal stress left to right if you view from the top. And then, I forget what's the direction of the twist. Maybe something like this. and going this way and going this way. So that was the point that we're dealing with. If that point is on the very top, then we don't need to care about transverse shear because it's at the very top if we are working on that point. However, since I have a pulley force right here, so in the first homework, we need to investigate shear diagram along this plane and also along the horizontal plane, right? So in fact, you do have a worse position somewhere at the horizontal plane. Because it's like the two coordinates, right? And what you need to do, in fact, was you need to figure out what's the moment along on the y plane and what's the moment on the z plane, and you need to sum them up. So you will realize, okay, actually the total moment is somewhere at not in parallel with y or z. It's like having an angle. So it's like you're studying some point on the side with the angle. The issue about that problem was, since we are not studying the very top point, so we do need to talk about this. The problem is, even though we know we need to talk about this, it's very troublesome. Because we now are facing a plate that lies on the surface. So it's like you are working on a particular coordinate, like a working plane. However, when we are studying transverse shear, we are studying in a horizontal plane. So they are forces or stress on different planes. You cannot directly sum them up. So on this particular point, it's no longer a plane stress problem because you have stress outside of the plane. If we don't need to talk about transverse shear, it's easier because torsion is always like working on the tangent plane, and normal stress is going this way. So no matter where we stand, it's a plane stress problem because the torque goes around, right? You can study here. The torque is like this, and you're fine because it's still stresses on the plane. However, when this comes into the story, you are introducing stresses in a different plane. It's no longer a plane stress problem. It's something I don't want to deal with. So in that particular homework, I should add one more sentence, assuming transverse shear to be 0. Otherwise, you need to work on it. Okay, so that student helped me to polish my homework. So if I truly want you to study transverse shear, I will definitely not deal with a problem like this. I will focus on single plane. So everything remains on a plane. Then you can do 2-dimensional more circle. Otherwise, you need to deal with 3 principal stresses. I don't even know how to. This is very, very troublesome. Okay. Thank you for the question. Okay, I think the time is up. That's it for today. Do we do attendance check?
还没，
Okay.
我发多面了。
So please, you do attendance check before you go. And if you still have questions, you can come to here. That's it for today. Okay, 我再说。 Anyone has any other questions? You can come here.
the